Okay, so we have another area under the curve example, and if you haven't watched it yet, I would highly suggest that you watch the previous example where we kind of went over more in depth and talked about more what is an integral and how does that apply to area under the curve. Because now we're going to kind of jump through some of those concepts when we get there, and it's a little bit shortened version. So they gave us the function g of x is 1.5x minus 8. And similar to what we did in the previous one, first they want us to use our nice engineering paper and graph it on a 1-to-1 scale where each block is 1 point, and draw it all out between 0 and 16 and see what it looks like. So again, the behavior we would see of this is that it starts at -8. It has a slope of 1.5, so every 1 it goes over, it goes 1.5 up, or another way of saying that is every 2 it goes over, it goes 3 up. So we can kind of plot those points along the way. It crosses somewhere here between 5 and 6. We know at 10, if you want to calculate, you get 7. Our endpoint at 16, you can calculate that out, but you actually get it that point is 16, 16. So that's kind of what our graph would look at there. And now what it wants to know is what is the area under the curve from 1 to 12. And so if we take our point 1 here, and we'll draw that spot, and then we take 12, which would be right here, and draw that spot. It wants to know the area under the curve. And when we say area under the curve, we generally mean above the x-axis, or to the x-axis. So over here, it's just like what we had in the other one. It makes perfect sense. It's this shaded area, right? But this part, there's no area above the curve. The curve is under. And so what actually happens here is we talk about this area, but where this gets us a positive number, this is going to actually be a negative number that we have to worry about. So this area under the curve is actually negative. We have a negative value of area there. And again, because this is a simple function, we could break this down using geometry. We could break it down by counting squares. I guess we could do that really quickly. If we take a quick count of those. And again, you might get slightly different when you count yours. I got about 13 squares here, about 34 squares there. So by squares, I get 34 in the positive minus 13. I'd get that our area should be 21. And again, what we could do is use geometry because we have triangles. So yeah, we could use some geometry. We get this upper square, which is we first figure out this crosses at 5 1/3, so this width here is 6 2/3. The height is 10. For this triangle, we have 5 1/3. Sorry, it's only 4 1/3 because it doesn't go all the way over. If we use that in there, we get that it's 4 1/3 that way. This height is 6 1/2. So we calculate those triangles by base times 1/2 base times 5, 1/2 base times 5. We can get those, do some quick calculations. I know it's a little messy for you to see. Well, we'd end up with 19.25. So geometrically we can get it, but again, that's not the best way to do it, so that's why I don't care if you're able to read that. What we want to do is by using an integral. So for using an integral, we know that the area is the integral from 1 to 12 times g of x dx. And then we would use our function and some antiderivatives and keep simplifying that. Okay, so we put our function in there and we're evaluating from 1 to 12. And some of the things we learned from the previous work is that we know we can do each part by breaking it up. But again, as we get more comfortable with that, we don't need to actually write out the steps of I'm going to do this part first, I'm going to do that part second, and splitting it up in all the different parts. I can just do it as one big unit. And so I can do the antiderivative of each of these parts as I go along. So I know this integral from here to there is the antiderivative of that, which is I can keep the coefficient. I'm going to take the power and raise it by 1 and divide by that new power. So x to the first becomes x squared. I divide by 2. Minus 8. If I don't have a value there, I'm going to raise, that's the same as x to the 0. I'm going to raise it 1, and it's going to become to the x. And then the other thing I learned from the previous part is that for antiderivatives in general, I would have to have a plus c, but because whenever I'm evaluating it between 2 points, I don't have to worry about that because they would just cancel each other out anyway. I can actually just stop there if I'm evaluating from 1 to 12. So to evaluate this, I would do the antiderivative of that to that. And again, if you're not sure if you got the antiderivative right, go back the other way and make sure it makes sense. If I took the derivative of this, would I end up back there? If I took the derivative of this, I would multiply by 2. That would get rid of the half on the bottom. I would subtract 1 from there. That would just give me to the x, so 1.5x. If I took the derivative of this, I would multiply by 1, subtract 1 from it. I would end up with x to the 0. So negative 8 times x to the 0 is negative 8. So that works. Now I have to evaluate it at each of those portions. So the area is equal to, what do I get when I put in 12? Minus what I get when I put in 1. And then we'll do some simplification. So to simplify this a little bit, I'm going to square that term, square the 1. 1.5 divided by 2, a better way to write that is 3/4 or 0.75. Either way I want to do that. Maybe it'll make more sense. Let's just make it 0.75. So one more step to simplify this. So to simplify that, 144 times 4/3 is 108. I've still got that minus 96. 3/4 minus 8 is negative 7.25. So I get 12 over here, minus a negative is plus 12.25. And so I get 19.25 for my answer, is my area. Again, not real close to what I got there. This is why you don't just count squares. It's tough to do to get it accurate. It is what I got when I used geometry. So by doing a little bit more thinking, so it actually is probably right. The key concept here being that for any function we have, I know we've only used linear functions so far because they were easy, but any function that we can do the antiderivative of, we can get an area under the curve.